we'll see the working of narrow band stop filter. Now here we are utilizing a 20 circuit. The basic circuit diagram of this is, now this is a 20 circuit consisting of one T comprising of R, R and 2C. The other T circuit is C, C and R by 2. So here itself we'll get the narrow band stop action. So the frequency response of this circuit happens to be like this, so which is designed for a center frequency of 10 kilohertz. So you can see here we'll get a frequency response of this type, which is exactly the band stop filter action. So we'll get the center frequency around 10 kilohertz, but the Q factor of this one, the bandwidth of this filter happens to be large, so we can reduce the bandwidth or we can increase the Q factor of this filter by giving the feedback to the same circuit which is there in the modified circuit. You can see this is a modified circuit of the same band stop filter, which we'll now call it as narrow band stop filter. Why means the bandwidth is reduced, which eventually increases the Q factor of the circuit. So this is one emitter follower, this is the other emitter follower. So this resistor R, X and RY will decide on the amount of feedback we are giving. So by adjusting values of these two resistors, we can adjust the FH and FL, the bandwidth of the narrow band stop filter. So you can see the frequency response of this 20 circuit without any feedback happens to be so and so. So when we give the feedback, you can see it has become narrow, the bandwidth has reduced. So that's the improvement of this circuit over the ordinary 20 circuit. Suppose if you are having any problem in the output, first thing is that you first rig up this circuit, ensure that you are making proper connection using this 20 circuit. So if you just verify the input output relation, you will certainly have the band stop action. So you can go for this next connection, which will improve the bandwidth of this one, so which will reduce the bandwidth, which will increase the Q factor of the band stop filter. Now I'll see the working of that one. Now since we are using a voltage follower whose gain happens to be 1, so we can keep the input voltage any value. It's nothing like in your narrow band pass filter. Since the gain was 10, we have to keep the input voltage around 2 volts. Here it can be any voltage because the gain happens to be just 1. So we have kept the input voltage around, okay, let me just keep it around 10 volts. So this happens to be, now this is around 12 volts, so 6 divisions into 2, the input is 12 volts. Now you can vary the frequency. We know that first, before we start taking the reading, let us just verify whether that band stop action is happening or not. So the frequency is now around 2 kilohertz because we are expecting the center frequency of the narrow band stop filter happens to be at 10 kilohertz. At 2 kilohertz, the output amplitude should be equal to the input. You can see that, you can see it over here. Both are there in 5 divisions. You can just coincide both of them. You can see their amplitudes are almost same. So this is also in 5, this is also 5. So this is your input, this is the output. So both the amplitudes are almost same because I'm there in the pass band of the band stop filter. Now as I increase the frequency, so this is with that feedback connection. As I increase the frequency, you can see what we are supposed to have is it should reduce and it should become minimum at the center frequency, and it should again increase. Before we take the reading, let us just verify whether that stop action is happening or not. You can see the output is started reducing. So here you can see this is the minimum value. So if I slightly go beyond this one, output voltage again increases. So you can easily identify at what frequency it is minimum. So this is the minimum frequency, this is the minimum amplitude which corresponds to F0. The corresponding frequency we can get it from either from this one, noting the time period of the waveform, or you can get the same thing from your DSO. So let us identify where it is minimum. Okay, here it is minimum. You can clearly make out what is the frequency. The specification happens to be 10 kilohertz. We are getting 11.4 kilohertz. Okay, there will be slight deviation from the design value because of the tolerance of the RNCs. So we can have one of the reading of your narrow band step filter at FC. It is 11.42. This is in kilohertz. My output voltage happens to be, it's 2 into 4 volts. So this is totally 2 into 2 divisions 4 volts. The input voltage was at 12 volts. You can say this is the output voltage. So we noted this particular position. So in order to find the bandwidth and all those things, you find what is V0 max at this point and V0 max in this passband, because there are two possible passbands. We need to find what is V0 max here, V0 max over there. So let us find V0 max by reducing the frequency below F0. So I reduce the frequency below F0. Now it's around 2 kilohertz. Let us identify what is the output voltage. The output voltage happens to be 12 volts. Input is there at 12 volts. Input is also, input is slightly more than 12. Okay, let me further reduce the frequency and see what is the. Let me first measure the input voltage. Let me make it 12, because when we measure the output voltage, input voltage is 12. Let us make it 12 volts. Now input is 12. Let us measure what is the output. So output voltage happens to be 10 volt. So at a frequency of 2 kilohertz it is on. So let me further reduce the frequency, because we need to go to pass band. So it's almost 10. Now the frequency is around 427 hertz. This is 427 hertz. The output voltage is 10 volt. That's exactly my V0 max 1. Let me just measure that as V0 max 1. Okay, you can find the frequency, which is 0.707 times of that, which gives the higher cutoff frequency FH. So that you can know from this. So what is 7.707 of this? So you need to get a voltage corresponding to 0.707 volt. You find what is that frequency. So that frequency at which you get this amplitude, output amplitude, keeping the input voltage 12 volts, happens to be the higher cutoff frequency. Do the same thing on the other side of your FC. So let me make the frequency beyond 11 kilohertz. So the frequency is now, it's around 22 kilohertz. Let us now find what the, okay, let us first adjust the input voltage, that is there at 12 or not, because we need to keep the input voltage constant at 12 before we make any measurements. Okay, input is adjusted to 12 volts. Let us see what the output. Output is slightly reduced. So output happens to be now 9 volts. So other V0 max. So let me write it that as V0 max 2. That is around 9 volts at a frequency of 22.8 kilohertz. That's it, is this passband. Now let us again find one more frequency corresponding to 0.707 of this 9 volt, which happens to be 0.707 into 9. So the frequency corresponding to that happens to be the FL. So this is FL. At this corresponding frequency, the output voltage is V0 max into 0.707. So we can find what is FH and FL. We'll be knowing F0. So in order to find the Q factor, you substitute F0 by bandwidth, where bandwidth happens to be FL minus FH. So you can verify what is the Q factor. Of course, you're going to have a theoretical equation for this FL and FH, which depends on the feedback factor. So as I showed in the previous circuit, so according to this circuit diagram, these two resistors will decide what are the FL and FH. So you can just verify the theoretical and practical values of FL, FH from this one. Of course, for completeness of the circuit, the frequency response, you can take few readings. Now these are the typical readings. We need to take 5 readings, one at F0, one for V0 max 1, other for V0 max 2. The other one will be 0.787 of V0 max 1 and 0.787 times of V0 max 2. So these are the 5 critical readings to find out the center frequency and the bandwidth. You can take few more readings over here, here and in the pass band, so that you can have a smooth graph in the frequency response.